Yes, last week we dealt with how to define a random experiment, then learned how to define the sample space, got to know events, which are subsets of the sample space omega, and assigned probabilities to these events. And this week we want to expand the concepts a bit further, particularly the concept of random variable, which is related to probabilities. We will soon see an example where we can observe the advantages of this concept, and with distributions, both discrete and continuous distributions. But let us start directly with an example to understand why it can be meaningful to introduce the concept of a random variable. So, our example is the following. You have two dice, and you want to measure the sum of these two dice. And what we do for that is that we first define our sample space. And one possibility would of course be to simply define the sum as a result. What is better suited, because all these events are equally likely. What we could do to create a Laplace experiment, so to speak, is to write the actual numbers of the two dice as tuples. So, in other words, the possibilities are 1.1, 1 to 2, up to 1.6, and then we continue with 2.1, 2.2, and so on, until we eventually reach 6,6. Can you briefly consider how many possibilities omega has? There are 6 for the first die, and 6 for the second, so there are 36. And all these variations are equally likely. This makes it easier for us to calculate. So, this is our sample space. And now imagine the following situation. You might have a game where the goal is to determine a sum of the dice that is greater than or equal to 10. And I now give you the task of determining the probability that the sum of the dice is greater than or equal to 10. And if we do it the same way as last time, then we will do the following. We are now looking for the event that describes the sum greater than or equal to 10. Let's do that. It would be the sets, so 5.5 would definitely be correct, 5.6. And 36 cases in total, just as we have in the classical Laplace random experiment. Yes. Now let's imagine that we want greater than or equal to 11. Then we would have to do exactly the same thing again. We would need to find this event A again. And it seems somehow more sensible to store this concept of the sum of two dice rolls in some way, rather than having a separate variable. That means we can simply say that the sum variable must be greater than or equal to a number. And that is exactly the idea of the random variable, that we can store the concept of the sum of two dice rolls in a so-called random variable, and then simply write the probability that the random variable is greater than or equal to 10, which we want to determine. So today we will discuss what, in a mathematically precise sense, such a random variable exactly is, and we will introduce that right now. And then we will try to understand again how it relates to the example we just saw. It is actually a bit abstract. So a random variable is not a classical variable, but rather it is a function. It is therefore a function that belongs to a random experiment and can assign a real number to each elementary event of this random experiment, that is, to each element from omega. That is, we have a function that maps from omega to r, and then we write that little omega is mapped to x omega. And that's a bit strange now, because before we said a random variable can be the sum of two dice rolls. And we want to illustrate this again using this example. So this is our omega. So we have these tuples. Just briefly, why is this omega? We have the tuples where x is between 1 and 6 and y is between 1 and 6. And now the question is, how do we define this function? And we do this as follows. We say that when we substitute this number x, y, this is indeed an element. So x, y is an element from omega. This should be x plus y. That is a real number. So let me give an example with numbers. So if we now assign the number 1.2 to x, we would get the number 3. And that is exactly what we do. So we substitute something into omega, namely, for example, such a pair, and get a real number out. That is, the function that assigns x, y, and x plus y is nothing other than the concept of the sum of the two face values. And now you can consider that you can, of course, introduce additional random variables. For example, you can also take the maximum of the two numbers. Then you have, so to speak, the maximum. For instance, let's make an example. In this case, x would be 1.33 because we would take the maximum, or also the difference of the values, x minus y in absolute terms. That would also be a question you could ask. What is the probability that the difference between x and y is greater than 1 or so? That would then be the corresponding question. This means that we can define the concept of a random variable as a function. And now comes the trick, how we can assign a probability to this. Now, if we have such a certain random variable, we can define events, specifically the following. So we have a random variable x, we have a sample space omega, and we have the following: r, and we have an x, which doesn't matter here. We have an x that is an element of r. We are looking for any number. For example, we will make an example shortly, then we can express the event. I will write this in parentheses to clarify that x equals x is not an equation, but rather an event. So, this here, an event, is therefore to be understood as a subset of omega. Nothing else is an event. And that is the subset such that if I take all elements from omega, when I substitute the element from omega into x, x comes out, and that seems very complicated. So I will provide another example here. X is equal to 3. Let's take a look. And imagine that x is the sum of the double dice rolls. X is the sum of the double dice rolls. And the event we are now looking for is the set of all combinations of dice rolls that result in 3, and that would be 1, 2, and 2.1. Because there are no other possibilities to get a 3. And so this is now the event x equals 3. And now you can already see, I can of course assign a probability to this event. And we can do the same. We will now provide another example. We can also have x less than or equal to 3, which would be this event here. We can also describe this. So now all outcomes are such that the sum of the dice rolls is less than or equal to 3. That means we still have these possibilities, but also the 1.1, because that is less than 3. And we can just as well do the whole thing for x less than 3, but also for x greater than or equal to 3. or greater than 3? Yes. So it sounds very complicated, but basically the idea is that I have a random variable and then I try to find those elements such that when I substitute them into the random variable, the whole thing is less than, equal to, or equal to a certain number. And that itself is then again an event, and because it is an event, I can also assign a probability to it. And yes, so take another good look at that. It's a bit more complicated, but I think with the example of the double dice roll, it will become a bit clearer. And now in the next video, we will look at how we can introduce distribution functions with these random variables. Until then.